Unit 15, Part 11. So the proof I'm about to work out, you will find Klenk has worked out on 286. I'm going to do it slightly differently to her, but I want to go through it so you see it, how it's produced. So that's the way she does it, and focus. You'll notice that in steps, look at steps 4 and 5. So we're up to step 3. We've got that flag A already. Steps 4 and 5, she does the instantiations and then she sets up for conditional proofs. I'm going to do it differently. She's taking note of the parts. Very good. What part are we up to?
Part 3.
10.
Part
11. 11. We're up to part 11.
What? Did I skip any pieces?
Yeah, I think we missed a bit. Anyway, so there's an advantage to doing that first. So something I don't think I stressed enough in the Unit 9 lectures, but
What are we part again?
11.
10?
11. This is 11. Formulas that are derived within subproofs cannot be appealed to outside of the subproof, right? Once you've discharged an assumption, so think of a conditional proof. Once you've discharged an assumption, you cannot appeal to. And if you discharge, a lot of the subproofs you've seen, both for conditional proof and indirect proof from Unit 9, and a lot of these ones, you have a subproof. Here, there's subproofs for universal generalization as well as conditional proof and indirect proof, but a lot of the time the subproof ends and then you've got the conclusion of the overall proof and that's it, right? This one's going to be like that, so it's not going to matter, just why I'm going to do it slightly differently to her. But there's a general advantage, general strategy advantage the way she does it, doing the universal instantiations for these two premises before she sets up for conditional proof. Namely that they're on a more epistemologically secure line, right? They're over here as opposed to being, what I'm going to do, I'm going to set up for the conditional proof, like seeing this as a conditional, remaining conclusion driven, set up for conditional proof, and then do the universal instantiations, which is not going to matter here, but I'm trying to say why there's an advantage to what she's doing, right? If the proof was such that,
You need this?
if the proof was such that you completed a subproof, right? So think of when you're trying to prove a biconditional. How do you prove a biconditional, right? You prove a biconditional by the general geometry to prove a biconditional, right? A biconditional B is, right, this is the main line, you assume A, you derive B to get A hook B on the main line, you assume B, you derive A to get B hook A on the main line, and then you conjoin A hook B and B hook A, right? Conjoin them to get this by a biconditional exchange, right? So here's an example of a proof where you've got a sub-formula, and the proof doesn't end when the sub-formula ends. You keep going, right? There's going to be many proofs like that, especially for the mixed quantifier ones, right? You're going to be setting up sub-proofs, deriving a certain conclusion that you need to then keep going and derive more stuff. So we'll see a few of these, or you'll at least see a few when you read through Klenk. For problems for which that's true, where the end of the subproof is not the end of the proof overall, there's an advantage to doing what Klenk does, right? Deriving whatever you can on the line as far to the left as you can, right? Deriving it before you put it in a subproof. Because say here, for example, right? Say I had, not A or D, right? This is equivalent to A hook
Wait, what about this?
D by conditional exchange. It would be better here to put this up here, right? Because now, when this formula is here, it can be appealed to, both within here and within here.
To his garden
But say I didn't do that there, and I did the conditional exchange of this inside this subproof.
This one is the door.
Then
Those are the footsteps.
here, and also in here, on this main line and here, I would not be able to appeal to that. Right? So if I needed to appeal to this formula out here, I'd have to derive it again. Right? You're not allowed to appeal to formulas within a subproof once the assumption has been discharged. Okay, that's why it's an advantage to the way she's doing it. It's not going to matter here, so I'm just going to do it in a different order. Okay, so that's your conclusion, right? So I'm going to not show that again because, right, now I'm aiming at this. This is the instance from which I need that, right? This is the conditional. I just did the opposite of instantiation, going from that to that. I use the advantage that UG has that's like the conditional proof advantage. Namely, I know exactly what instance I need to get to that, so I know that I put this instance down so I know where I'm going, and I know when I've completed my subproof. Okay, so now that's all you have to worry about. That's all you need to look at, really. So that's fine that that's there. GA hook, not ZA. Okay. It's a conditional. I'm going to use the form of that to set up a conditional proof, right? So I wanted to show you this so you see how a CP appears inside a indirect proof. And just before so I don't forget, after you've seen this, you should look at page 292 where she presents you side by side with two of the proofs she's gone through. J is the one we're actually doing. And you'll notice here that the proof on the left is a CP inside a UG, whereas the proof on the right is a UG inside a CP, right? So don't freak out, both of those are possible. Once again, it's always just attend to the form of the thing you're trying to get, right? If the very last conclusion is a universal statement, then universal generalization will be the outside subproof, right? We're setting up for UG. Now, when you set up for UG, like we're doing here, you write the instance down from which you're going to be doing the UG, right? And you just attend to the form of that thing. And if that's a conditional, now you set up a conditional proof. In the other example, which is N, right? And she runs through it on another page, but then she's just comparing the basic geometry or structure of it for you there. In N here, let's take to page 292, right? Why does it have the opposite structure? Why has it got a UG inside a CP? The answer is very simple. The conclusion, which you put down first, is a conditional. So you set up a conditional proof, right? And you've assumed the antecedent for all x fx. You put the consequent down the bottom, and then you looked at the consequent. That's the for all x hx, right? And she's just then asked, what's the structure of that? That's a universal statement. I'm going to get it by UG, right? So again, it's just look at the form. Let that determine what rule you're going to use, right? And then now you know what conclusion you need to complete the proof. Look at that formula. What is its form? In this case, from UG to a CP. Okay. All right. So we flagged a. Okay. So did I set up? So I'm going to set up the CP as so. Set up a conditional proof, assume my antecedent, right? It's the individual statement GA. Don't forget, CP, put the consequent down the bottom, right? Know exactly what you're going for. Not ZA.
That looks like a perfect.
Okay. By the way, perfectly legitimate. You could set up an indirect proof for this. You could assume ZA, or ZA, as you'd say, right? Derive a contradiction. And then infer this by IP. Yep, another there's no limit to the number of subproofs within subproofs you can do. Okay, so now I'm going to do the universal instantiation. Notice that my order is slightly different from the way Klenk presents it. For reasons I mentioned before. So we got 5, 6, still not going to fit it. 3, 4. Okay, it's F, A, or G, A. You've got to turn it off. Right. Sorry. You can take it outside, mate. Take it outside. And then you can turn it back. Sorry, you can turn it back on again, okay?